I am Fabio Messina, groom artist and creature effects artist, and this is the second video for the Godfeather project, a Houdini toolkit for feather grooming. In the first part, we looked at the feather guides and the feather generator. In this second video, we will focus more on the grooming aspects, showing the barbs generation and exploring the endless possibilities for procedural grooming made possible by this toolkit. Before jumping to a demonstration of how the grooming nodes work, let's go for a quick overview of the general architecture. In the Godfeather workflow, feather geometries are fed into an object called feather system. A feather system is a complex node that contains a recipe to build a feather on each feather geometry. We could say that a feather system defines a class of feathers. A subnetwork inside of the feather system builds the recipe using the Godfeather nodes. Godfeather nodes used inside of a feather system are the barbs operators and the value operators. Barbs are generated and processed by barbs operators. These are SOP nodes which perform operations on the incoming geometry and output the processed geometry. They have parameters to tweak their effect, but they also have special inputs that can override the constant parameter on the UI with a highly flexible logic defined by the user. The nodes used for this purpose are the value operators, and they are like meta nodes as they carry information logic for the barb operator they are connected to. They can also be combined together. Value operators are like functions applied to specific domains. Being able to define the look of your feather spanning across domains is really important. Many feather tools give the user an already rigid choice of what can be customized and how. In the live demo, we'll see that the toolkit will let you handle a perfect separation of domains. In this architecture, they are the spine domain, the barb domain, the feather domain, and the word space domain. Let's move on and see all of these in practice. For this demo, we will start with a simple feather groom created with a few guides and a feather generator. The first step is creating a feather system object node. This node will reference the feather geometries and will generate actual feathers based on them. Let's have a look at what is inside this feather system. The generation process is organized in macro steps: the generation of barbs and quills, the main logic for computing barbs direction, further processing of the barbs with effects like noise or curl, and finally the output geometry being put together. We start feather creation setting values on the barbs generator. Barb's absolute width is the dimension we deal with during this process. The density to have coverage on the whole feather is being automatically computed. We can also set a percentage of cut for the spine, subdivisions for the barbs, and an additional density multiplier. The barbs generator can also create fake barbules. Fake barbules are strands built on each side of each barb to mimic the look of the barbules without the huge cost of generating thousands of primitives. These can improve dramatically the realism of feathers when seen from medium distance and even in close-ups. You can adjust the relative thickness of barbs and fake barbules, assigned to different shaders. This will give the look dev artist the ability to find the perfect balance in terms of shading in order to match the proper light response. We now move to Reiki's generation, and in doing so we will start seeing more of the Godfeather paradigm and the way it gives the artist creative possibilities. In this example, we will set the thickness of the rakeys using the external input. We create first a float constant node and plug it in the width input. Let's use an exaggerated value to make everything more visible. We also might want to have thinner rakeys for smaller feathers. In order to do this, we can use a feather attribute in this network. Feather primitives are coming from the generator with some pre-computed feather attributes. In this case, we are using f-length to have the thickness of the rakeys proportional to the size of the feather. And if the effect is not strong enough, we can use another multiply node to make the dependency quadratic. We can also blend between these and other solutions, as we will see later. The next step in feather creation is the base orientation for the barbs. The barbs orient node has the parameters to set the inclination and the shape of the barbs, but again, we can connect this node to special Godfeather nodes to build more complex behavior. Here we are using a feather ramp, something that you will use quite often when working with feathers. This ramp can refer to the spine domain or the barb domain, and it can be plugged to anything, and also being driven by anything. In this case, we are using a barb ramp connected to the barb shape input. We want to fix this shape on the tip, which doesn't look good. To do this, we simply create another barb ramp and we use a blend node. The blend node is driven by a spine ramp. Any other Godfeather node could be used to build this procedural shape. We're starting seeing a bit the philosophy behind the toolkit. The UI on the nodes which perform operations is minimal. It's not prompting the user with countless options, because ultimately it's the artist building whatever he wants using these special nodes. Another important element for realistic feathers is recreating the splits you can see where barbs disconnect from each other. To achieve complete procedural control on this aspect, we use this cloud-shaped node. The Barbs Align Gaps node will provide the Barbs Orient with the logic for creating this effect. You can set the density and the distribution of the splits. You can also set how likely some of the gaps can be overlaps instead. And of course, you can use the Godfeather nodes for a more refined procedural creation of this effect. In this example, we are using a barb attribute generated by the splitting process, the segment ID, to randomize the depth of these splits. We connect a feather ramp to the push intensity input, and as the ramps give the user the possibility of being shifted or scaled, we randomize the scale effect using the segment ID as a seed. And finally, simply using another multiply node will give us a normalization of the push effect, giving smaller gaps a consistent look. When looking at multiple feathers, we can see that the distribution of the splits is the same. We simply plug the ID feather attribute to the seed, and we have complete randomness for the whole feather system. If you are working on a hero character for film, you will likely need to fine-tweak any small aspect of the feather groom. We can add another feather attribute to drive the seed for the generation of the splits. Let's pick a meaningful name like split seed left. And now we can go back to our feather geometries and use another Godfeather groom node to edit the feathers one by one. We just need to create the attribute on the feathers and change the value. This gives the artist the ability to pinpoint what needs to be changed, and this can be done super fast interactively on the viewport. As long as you use attributes in your feather system, you will have a setup where anything can be driven using maps, guides, or individual tweaks. We can move now to Barbs processing, with operations like curl, noise, cut, and any sort of breakups. First, it's a good idea to slightly offset the overlaps coming from the alignment process in order to prevent artifacts. We use a Barbs curl node. The curl operation bends the barbs in relation to the feather normal or the feather surface. In this case, we simply want to push the segments created by the overlaps to prevent intersections and give the feather a more natural look. We can also use the curl to create a ripple effect, and as always, the ability to combine this with any other Godfeather node gives us full control. Let's see how we build a noise effect combining the features of the toolkit. We create a Barbs noise node, we plug the feather ID to the noise offset to make all feathers get a different looking noise. Then we connect a feather attribute to the intensity. Now we'll be able to drive the noise intensity setting the value of the attribute. This can be done in different ways. We can paint a map and tell the feather generator to transfer the value from the skin. Or we can create the attribute on our guides for it to be interpolated when generating feathers. And we can always use a Godfeather groom node to edit the value on individual feathers. In this last segment, we will see how to create a composite effect. We start adding a barb attribute that we are going to use as a mask, and we connect a value noise operator to the input plug. Now, after tweaking the noise parameters to achieve the kind of mask we want, we have these small chunks that we can process to create a damage effect. Using a cut node and the barb attribute operator, we can trim the masked barbs. And connecting the same attribute to a noise node, we have our composite effect of damaged feathers. Of course, we don't want all feathers of our system to look like this, so we set up a random constant and a threshold to activate the effect. And we can manipulate the seed or the threshold, adding other constants or attributes. This was the last example of this demonstration. Hope you got interested in the Godfeather workflow, in its potential, and the other creative possibilities beyond the ones shown in this video came to your mind. Thanks for watching.